tires on a car or the fabric in the shirt you're wearing, they are perfectly uniform. But if we trace their timeline backwards, we find something entirely different. A sleek, perfectly balanced tire devolves into nothing more than sticky, dripping tree sap in the middle of a jungle. Nature is chaotic. Raw organic materials grow in the dirt, completely subject to the unpredictable whims of weather, soil chemistry, and manual harvesting. In nature, no two plants are exactly alike. But when we buy a product off a shelf, we expect exact replication. We demand parts that fit together to the millimeter, fabrics that behave consistently, and materials that survive thousands of miles of use. So how do we bridge that gap? How do industrial engineers take the messy unpredictability of an organic harvest and force it into a flawless, mathematically precise mold? We can see the answer by looking at two extreme transformations. First, how rigid bamboo stalks in wood are broken down to create soft, wearable clothing. And second, how liquid sap dripping from a rubber tree is manipulated into a nearly indestructible vehicle tire. Modern manufacturing is a high-stakes effort to harness physics and chemistry, stripping natural resources of their original properties to fit a specific human need. To create a soft textile from wood, factories first have to gather the raw material in staggering volumes. Massive fields of felled logs wait for processing, and none of this dense, rigid timber looks anything like clothing. The first step is brute force. The rigid plant matter is mechanically shredded, tearing solid logs apart until all that remains are tiny splinters. Mechanical force isn't enough to make it soft. Splinters are submerged in an intense chemical bath. The solvent strips away the tough cellular walls holding the plant together, leaving behind a thick, uniform paste known as cellulose pulp. The plant's original geometry is completely dissolved, reduced to a fluid state. This liquid cellulose is pumped through a spinneret, like a microscopic showerhead. Squeezing through tiny holes, it hits another chemical bath, instantly solidifying into long, flexible threads. The original plant is now entirely gone. Engineers have manipulated its cellular structure to create a soft, wearable fiber out of solid timber. The challenge with raw tree sap is the exact opposite. Natural rubber is sticky, soft, and melts under heat, making it useless for bearing the weight of a car or surviving friction against asphalt. To make it strong enough for the road, engineers use a chemical process called vulcanization. Natural rubber's polymer chains sit loosely, sliding past each other and causing it to melt. Inside pressurized ovens, the rubber is baked with sulfur. Heat makes sulfur atoms snap into place, forming bridges locking the chains into a rigid grid. Once those molecular bridges are formed, the resulting material can be pulled from an industrial press in a permanent, uniform shape. It can now support thousands of pounds of steel and endure extreme friction without losing its form. If we didn't force that specific chemical reaction between heat and sulfur, every vehicle on the road would sink into a sticky puddle of sap. Figuring out the chemistry to dissolve wood or harden sap only solves the problem for a single thread or a single tire. The next hurdle is doing it exactly the same way, millions of times in a row, with zero deviation. This requires massive rows of high-speed, automated machinery. By removing human hands, factories enforce strict replication across massive volumes of material. The environments where this happens are intense. They are loud, high-pressure zones filled with heavy mechanical impacts, extreme heat, and harsh chemical reactions. Yet the end result of this industrial violence is a clean, quiet product sitting under the bright lights of a retail store or dealership lot. Because we live in a friction-free economy where things arrive with the click of a button, we are largely insulated from the aggressive physical reality of the supply chain. The identical items we take for granted require massive engineering efforts to exist. They represent our ability to manipulate the basic building blocks of nature and bend them to our exact specifications.